Circular motion, exercise question 28, from H.C. Verma. Here is the setup. A cabin moves in a circle of radius r about center O with angular velocity omega. A table with a smooth surface is fixed inside the cabin at point A on the circle. A smooth groove AB of length L is cut on the table surface. The groove makes an angle theta with the radius OA. In the rotating frame, the particle at A experiences a centrifugal force m omega squared r directed radially outward along OA. We resolve this force along the groove. The component along AB is m omega squared r cos theta. Watch the particle slide from A to B under this acceleration. The question asks, a table with a smooth horizontal surface is fixed in a cabin that rotates with a uniform angular velocity omega in a circular path of radius r. A smooth groove AB of length L, where L is much less than r, is made on the surface of the table. The groove makes an angle theta with the radius OA. A small particle is kept at point A in the groove and released to move along AB. Find the time taken by the particle to reach point B. The key concepts. We analyze this problem in the rotating reference frame of the cabin. In this non-inertial frame, the particle experiences a centrifugal force equal to m omega squared r directed radially outward from center O, that is, along OA. Now, the groove AB makes an angle theta with the radius OA. So the component of centrifugal force along the groove is m omega squared r cos theta. Here is the crucial approximation. Since length L is much smaller than radius r, the position of the particle barely changes along the radial direction. So the centrifugal force remains approximately constant throughout the motion. This gives us a uniform acceleration along the groove, A equals omega squared r cos theta. Let us solve step by step. The centrifugal force on the particle is m omega squared r directed outward along OA. The component of this force along the groove AB is m omega squared r cos theta. Since the groove is smooth, the acceleration along the groove is simply A equals omega squared r cos theta. The particle starts from rest at A, so initial velocity is 0. Using the kinematic equation, S equals half AT squared, we write L equals half times omega squared r cos theta times T squared. Solving for T squared, we get T squared equals 2 liters over omega squared r cos theta. Taking the square root, T equals the square root of 2 liters over omega squared r cos theta. The answer. The time taken by the particle to travel from A to B is T equals the square root of 2 liters divided by omega squared r cos theta. Exam tips. First, whenever you work in a rotating reference frame, remember to include both pseudo forces, the centrifugal force directed radially outward, and the Coriolis force which depends on the particle's velocity. Second, in this problem, the Coriolis force acts perpendicular to the particle's velocity inside the groove. Since the groove constrains the motion, the Coriolis force only affects the normal reaction from the groove walls, not the acceleration along AB. That is why we could ignore it. Third, the approximation L much less than r is crucial. It lets us treat the centrifugal force as constant. Without this approximation, the force would vary with the particle's position, and you would need to solve a differential equation. Like and subscribe for more circular motion solutions at MAGPIEHUB.